In this lesson, we are going to talk about a very important topic in math, which is called Pascal's triangle. And using Pascal's triangle, how to expand binomials of any power. Now, Pascal's triangle is a triangular arrangement of numbers such a way that the vertex of the triangle is 1. Every row of the triangle starts with 1 and ends with 1, and every element within the edges is the sum of the two elements on top. For instance, if we go to the next row, you will see that it starts at 1, ends at 1, but the middle element is the sum of these two elements, which is going to be 1 plus 1 is 2. Now the next row is going to start with 1, ends with 1. Now the next two elements in between is the sum of the two elements on top. So 1 plus 2 gives you 3, and 2 plus 1 gives you 3 again. Continuing this process, we can generate as many rows as possible. So if we go to the next one, we get 1 here, and the last element is 1. Now 3 plus 1 gives us 4, 3 plus 3 gives us 6, and 3 plus 1 gives us 4. Now in a Pascal triangle, the first row is denoted with number 0. The next row is number 1. The row after that is 2, 3, and 4. And the column starts with 0. So this is column 0 on row 0. This is column 0 again, and this is column 1. This is column 0, column 1, and column 2. This is again column 0, column 1, column 2, and column 3. Again, column here is 0. This is 1. This is column 2, column 3, and column 4. So this is very important to understand. The numbering starts from 0 for row, and also for column starts from 0. The other property is that at every row, if you look at the designated number, for instance, let's look at this row. The number is 4. And look at the number of elements in this row. The number of elements is 1, 2, 3, 4, 5, which is 4 plus 1. The previous row, the number assigned is 3, but the number of elements in the row is 4. So the number of elements in any row is equal to the row number. But remember, the row that we are talking about starts from 0. The next example that we are going to do is we are going to expand a plus b squared. To expand it, I'm going to write this one as a plus b times a plus b. Then I'm going to expand a inside the bracket and b also inside the bracket. I get a times a is a squared, plus a times b is ab, plus b times a is ba, plus b squared. Now a squared, there is no like term, so it's a squared. ab plus ba gives me 2ab plus b squared. The next example is a plus b exponent 3. We have to expand it. So I'm going to use the fact that a plus b exponent 3 can be written as a plus b exponent 2 times a plus b. Now from the previous example, a plus b squared is a squared plus 2ab plus b squared times ab. Now I'm going to again multiply every element on the second bracket into the first bracket. So it's going to be this times this, like this, and this like this. So if you expand it, a times a squared gives me a cubed plus a times 2ab gives me 2a squared b, plus a times b squared is ab squared, plus b times a squared is a squared b, plus 2ab times b gives me 2ab squared, plus b squared times b gives me b cubed. Now a cubed, there is no like term. 2a squared b and a squared b gives me 3a squared b. ab squared plus 2ab squared gives me 3ab squared, plus and b cubed here. So a plus b cubed is equal to this expression. Just one thing very interesting is that if you remember, a plus b squared was a squared plus 2ab plus b squared. The exponent here is 2 and the number of terms here is 3. The other thing is that look at the way I can rewrite this expression on the right. I can write this one as a squared b exponent 0 plus 2ab plus b squared times a exponent 0. Now, if you look at the sum of the exponents of each term, here we have 2 plus 0. Here we have, remember, these are 1, so it's 1 plus 1. Here we have 2 plus 0. The sum of the exponents here is equal to the exponent here. And the other thing, if you look at it, you start with a squared, then it becomes a exponent 1, so it went down by 1, then it became 0. So again, it decremented by 1. At the same time, look at b. b starts from 0, then it went to 1, then it went to 2. We are going to use this fact when we talk about how to use Pascal's triangle to expand any binomial. Now, looking at the same thing for a plus b cubed. This is what we found. A cubed b exponent 0 plus 3a squared b plus 3ab squared plus a exponent 0 b cubed, which is exactly this one, but I added exponent 0 to the terms which is only 1. The first thing, the exponent here is 3. You have 1, 2, 3, 4 terms. So 3 plus 1 gives you the number of terms that you have to have in your expansion. The next one, every term has the parameters, the terms 1 and 2 of your binomial, a and b. Here you have a and b in every term. You start with the maximum exponent, which is 3, which is here. And then you go to 2, then you go to 1, then you go to 0. At the same time, the second term starts with minimum exponent 0, then it goes to 1, then it goes to 2, then it goes to 3. The only thing that we haven't talked about is the coefficient of every term. The coefficient here is 1, the coefficient here is 3, the coefficient here is 3, and the coefficient here is 1. Also, if we look at a plus b squared, which is here, the coefficient here is 1. You don't see it, it's 1. Then it's 2, and then again it's 1. So now if we can somehow relate the Pascal triangle with the coefficient, we are done. If you look at the Pascal triangle again, a few terms, the Pascal triangle goes like this one: 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Again, every term, like 2 is the sum of these two terms. 3 is the sum of these two, and this 3 is sum of these two. Now, if you look at the expansion, for instance, for a plus b squared, let's write the row number here based on the Pascal triangle. This is row 0. This is row 1, this is row 2, this is row 3. If you look at a plus b squared, the exponent is 2. So look at the row with number 2. If you look at the coefficient, you can see the coefficient is 1, 2, 1, which is exactly what the coefficients here are, 1, 2, 1. If you look at the expansion of a plus b exponent 3, the exponent is 3, so go to the row which has designated number 3, which is this one, and look at the terms here. You have term number 1 is 1. Look at the term here. The second term is 3. Look at the coefficient here. The next term is 3. Look at the coefficient here. And the last term is 1. Look at the coefficient here. So we finally got the idea how to expand any binomial with any power. What you have to do is that you have to start writing every term of the binomial starting with the maximum exponent, decrementing the exponent until you get to 0 exponent. At the same time, the second term starts with the minimum exponent and then increments by 1 until it gets to the maximum. And the coefficients, we can get them from the Pascal's triangle. Now let's do a couple of examples how to expand any binomial with any power. The first example is that a plus b exponent 7. The first thing I'm going to look at is the exponent here. Exponent is 7. As we said before, add 1 to 7, so it's going to be 8. So this means the expansion is going to have 8 terms. So let's say this is term 1, term 2, term 3, term 4, term 5, 6, 7, 8. Now I have to find the terms in the binomial. The first term in the binomial is a, and the second term is b. So the first term in the expansion is going to start with the maximum power of a. So it's going to be a exponent 7. And at the same time, the sum has to be equal to 7. So the next one, b, has to be exponent 0. The next term is a exponent 6, b exponent 1. A exponent 5, b exponent 2. A exponent 4, b exponent 3. A exponent 3, b exponent 4. A exponent 2, b exponent 5. A exponent 1, b exponent 6, and a exponent 0, b exponent 7. Now, we need the coefficients here. Since exponent is 7, I have to go and expand Pascal's triangle until the row is 7. So remember that the Pascal triangle starts with row 0. So this is first, then we get 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. If you want to know when you have to stop, just look at the number of terms. Here you have 4 or 5 terms. But in our expansion we have 8 terms. So still we have to continue. So 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, and 1. Now if you look at the number of terms, it becomes 2, 4, 6, 7. So we need one more. So 1, 7, 21, 35, 35, 21, 7, and the last one is 1. Now 2, 4, 6, 8, which is enough. So I'm going to put the first term, the coefficient here. The second term goes here. And obviously you put addition here. Plus 21, plus 35, plus 35, plus 21, plus 7, plus 1. And that's it. This is the expansion of a plus b exponent 7 using the Pascal's triangle. In the next example, we have to expand m minus n exponent 5. The first thing I'm going to do is to find out what is a and what is b. A is m and b is negative n. Now, since the exponent is 5, this means I have 6 terms. So this is my first term, second, third, fourth, 5, and 6. Now, the first term is going to be a with the maximum exponent, so m exponent 5, and b, which is negative n, 0 exponent. Then m exponent 4, negative n exponent 1. Remember that the sum of the exponents for every term has to end up to be 5. So the next one, m exponent 3, negative n exponent 2. The next one, m exponent 2, negative n exponent 3. Then m exponent 1, negative n exponent 4. And m exponent 0, negative n exponent 5. Now I need to find the coefficients. For this, I have to expand Pascal's triangle. So I'm going to have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and 1, 5, 10, 10, 5, 1. Since there are 6 terms here, I'm going to stop and I'm going to put these terms beside each term in my expansion. So 1 here, then 5 plus 5 plus 10 plus 10 plus 5 and plus 1. Now I'm going to simplify this one. So any number exponent 0 is 1, so this is 1, so I get m exponent 5. Then this term, negative n exponent 1 is negative n, so I get negative 5m exponent 4n. The next one, negative n exponent 2 is n squared, so I get plus 10m cubed n squared. The next one, negative n exponent 3 is negative n cubed, so I get negative 10m squared n cubed. The next one, negative n exponent 4 is n exponent 4, so I get plus 5m n exponent 4. And the last one, m exponent 0 is 1, so I get, and negative n exponent 5 is negative n exponent 5. So this is going to be the expansion of m minus n exponent 5. In the next example, I have to expand 2x plus 1 exponent 6. Here I know that a is 2x and b is equal to 1. And since the exponent is 6, I'm going to have 6 plus 1 terms, which is 7 terms. So it's going to be 1, 2, 3, 4, 5, 6, and 7 terms. We start with a with the maximum exponent, so it's going to be 2x exponent 6 and b, which is 1 exponent 0. Then 2x exponent 5, 1 exponent 1. Remember, the sum of the exponents it has to end up to 6. So 2x exponent 4, 1 exponent 2, 2x exponent 3, 1 exponent 3, 2x exponent 2, 1 exponent 4, 2x exponent 1, 1 exponent 5, 2x exponent 0, 1 exponent 6. The only thing I need is the coefficient, so I'm going to write the Pascal triangle. So it's going to be 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, and 1, 6, 15, 20, 15, 6, and 1. The last term, the last row I wrote has 7 terms, 2, 4, 6, 7, which means it's enough. So I'm going to put these coefficients right beside every term. So the first one is 1, so I put a 1 here. Then it's plus 6, then it's plus 15, plus 20, again plus 15, plus 6, plus 1. Now I'm going to simplify every expression. So I'm going to get, the first one that I have to do is 2x exponent 6. Now 2 exponent 6 is going to give me 64. 1 exponent 0 is 1, so it's going to be 64 x exponent 6 plus. Then we're going to have 2 exponent 5 times 6, which is 192, times 1 exponent 1, which is going to be 192, x exponent 5 plus. Then we're going to have 15 times 2 exponent 4 times 1 exponent 2. 2 exponent 4 is 16, times 15 is 240. So we get 240 x exponent 4 plus. Then we get 2 exponent 3, which is 8, times 20 is 160, times 1 exponent 3 is going to be 160 x exponent 3 plus. 2 exponent 2 is 4, times 15 is 60, times 1 exponent 4 is 60, x exponent 2 plus. 2 exponent 1 is 2, times 6 is 12, times 1 exponent 5 is 12x. And the last one, 2 exponent 0 is 1, times 1 is 1, times 1 exponent 6 is 1. So this is going to be our expansion of 2x plus 1 exponent 6. The next example that we are going to do is to expand y over 2 minus y squared exponent 4. Again, as usual, we are going to find what is a, what is b. A is y over 2, and b is negative y squared. Now, since the exponent is 4, this means I have 5 terms. So this is first term, second term, third term, fourth term, and fifth term. The first term is going to have a with the maximum exponent, so it's y over 2 exponent 4 negative y squared exponent 0. Y over 2 exponent 3 negative y squared exponent 1. Y over 2 exponent 2 negative y squared exponent 2. Y over 2 exponent 1 negative y squared exponent 3. And last, y over 2 exponent 0 negative y squared exponent 4. Now I need a Pascal triangle, so I'm going to write 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and 1, 4, 6, 4, 1. There are 5 terms here, and there are 5 terms in expansion. We are going to stop. We are going to put the coefficients as the terms of Pascal's triangle. Now the last thing is to simplify. Y exponent, any number exponent 0 is 1, so this is 1, so we get y exponent 4 over 2 exponent 4 is 16. Now the next term, we have 4 times y over 2 exponent 3. Y over 2 exponent 3 gives us y cubed over 8. So 4 over 8 gives you 1 over 2, so y cubed over 2, and there is a negative y squared, so we get negative y exponent 5 divided by 2. So this is done too. The next one is 6 times y over 2 exponent 2 times negative y squared exponent 2. So we're going to have 6 times y over 2 exponent 2 gives us y squared over 2 exponent 2 is 4 times negative y squared exponent 2 is y exponent 4. Now 6 over 4 gives us 3 over 2, so we get plus 3 over 2, and y exponent 2 times y exponent 4 is y exponent 6. So this is done too. The next one, we have 4 times y exponent over 2 exponent 1 is y over 2 times negative y squared exponent 3 is negative y exponent 6. Now negative 4 over 2 gives us negative 2, and y times y exponent 6 is y exponent 7. And the last one, y over 2 exponent 0 gives us 1. 1 times 1 is 1. Negative y squared exponent 4 gives us plus y exponent 8. So this is the expansion of y over 2 minus y squared exponent 4. The next example is another property of Pascal's triangle. Let's expand Pascal's triangle. So we have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. The sum of the elements of each, let's find the sum of the elements of each row. In this row, the sum of the element is 1. In this row, the sum of the element is 1 plus 1 is 2. This one is 1 plus 2 is 3 plus 1 is 4. Here we have 1 plus 3 is 4 plus 3 is 7 plus 1 is 8. Here we have 1 plus 4 is 5 plus 6 is 11 plus 4 is 15 plus 1 is 16. Again, if you remember the row, here is 0, here is 1, here is 2, here is 3, and here is 4. If you look at the sum, 1 can be written as 2 exponent 0. 2 can be written as 2 exponent 1. 4 is 2 exponent 2. 8 is 2 exponent 3. And 16 is 2 exponent 4. This means that the sum of the elements of each row of Pascal's triangle is 2 exponent row number. Row is 0. Look at the exponent here. Row is 1. Look at the exponent. Row is 2. Exponent. Row is 3, exponent, and row is 4, exponent. This means that if I expand Pascal's triangle and go to row n, and if I ask what is the sum of the elements in that row, the answer is 2 exponent n. Now we are going to talk about the recursive definition of Pascal's triangle. If you look at the Pascal's triangle, which is shown here, we said that every element like 6 is the sum of the 2 elements right on top. For instance, 15 here is 5 plus 10. So in general, if we look at any element, remember this is going to be in row, let's call the row number n. So the row is n, and the column to be r. We denote these two parameters here. So to denote any term in Pascal's triangle which is in row n and column r, we use this notation. This means term at row n and column r. For instance, for this element, the row number is 6, so we say T6. And the column here, remember the columns start from 0, so this is 0, this is 1, this is 2. So we say T62 is equal to 15. In general, remember that any element is the sum of the 2 elements on the top. Now, when you go one row backward, then the row number becomes n minus 1. And since we are adding two elements, so we have to write two terms here. One is n minus 1 and another one is n minus 1, the previous row. Now, if you look at, for instance, this element here, this is the sum of this 5 here and the 10 here. 5 is in column, the same column as 15. The column for 15 is 0, 1, 2, 3, 4. The column for 5 is also 0, 1, 2, 3, 4. So this means this element is Tn minus 1 and R. And if you look at 10, 10 is going to have the column 0, 1, 2, 3, which is one less than the column of 15. So this is going to be R minus 1. So in general, any element Tnr is equal to Tn minus 1 R plus Tn minus 1 R minus 1. This is, again, as we called, the recursive definition of Pascal's triangle. The next example, we have a series of dots here. We are supposed to write the number of dots in each diagram as a sequence. It is obvious the first one is only one dot, comma. The second one is 3 dots. Then we have 5, 6 dots. And then we have 4, 7, 9, and 10 dots. Now we are supposed to locate these numbers that we found 1, 3, 6, 10 in Pascal triangle and describe their position. If I write the Pascal triangle, it's going to be 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. If you look at the Pascal triangle, you can see that 1, 3, 6, 10 is here, or 1, 3, 6, 10 is on the diagonal here. So this tells you, if I continue with the same diagram, how many dots am I going to end up in the next diagram. If I continue with the Pascal triangle, I'm going to get 1, 6, 15, 20, 15, 6, 1. This means that the next diagram is going to have 15 dots. Now the next example is asking us to write an explicit formula and a recursion formula for the triangular numbers. The easy one is the recursive one. If you look at every term is the previous term plus the term number. Let's write the term number for each one of them. This is term 1, this is term 2, this is term 3, this is term 4. You can see, for instance, 3 is 1 plus term number. 6 is 3 plus term number. 10 is 6 plus term number. So I can write the recursive definition. Tn is the previous term plus term number, which is n. Now let's go and find how we can write the explicit formula for this example. To find the explicit formula, I have written the terms in a table of values with the term number n, and I'm going to try to find the relationship between n and t of n. First, I'm going to find the first differences. Let's call it d1. 3 minus 1 is 2, 6 minus 3 is 3, and 10 minus 6 is 4. It is obvious that the relationship is not linear because the first differences are not equal. Let's go and find the second differences. 3 minus 2 is 1, 4 minus 3 is 1. Since the second differences is the same, this means the relationship is quadratic. So I can write t sub n is an squared plus bn plus c. Now I have to find a, b, c. To do that one, I need 3 equations to solve for ABC. So I'm going to pick the first, let's say, first 3 rows of table of values, substitute back the values, and then solve for ABC. The first one gives me 1, which is t of n, is equal to 1 squared, which is 1. So a plus b plus c. The next one gives me when t of n is 2, when t of n is 3, n is 2. So 2 squared is 4. So 4a plus 2b plus c. And then last one says that when t of n is 6, then n is 3. So 3 squared is 9. So 9a plus 3b plus c. Now I have 3 equations. To find ABC, I'm going to subtract equation 1. If this is equation 1, 2, 3, I'm going to find equation 2 minus equation 1. This is going to give me 3 minus 1 is 2, 4a minus a is 3a, plus 2b minus b is b, and c minus c is 0. Then I'm going to subtract equation 1 from equation 3. This gives me 6 minus 1 is 5, 9a minus a is 8a, 3b minus b gives me 2b, and c minus c gives me 0. Now I have these 2 equations. Now I can go ahead and try to solve for a and b. To do that one, it is obvious that I have to multiply this equation by 2 and then subtract each other. So if I multiply the top equation by 2, I get 4 is 6a plus 2b, and the bottom one is just 5 is 8a plus 2b. Now if I subtract the top equation from the bottom equation, I get 5 minus 4 is 1, 8a minus 6a is 2a, 2b minus 2b is 0. From here, I get that a is 1 over 2. So this is a. Now we are going to sub it back in either one of these equations, in these 2 equations, to find b. I'm going to pick the first one because there is no coefficient, so I get 2 is 3 times a. A is 1 over 2 plus b. So from here I get b is 2 minus 3 times 1 over 2 is 3 over 2. 2 can be written as 4 over 2 minus 3 over 2. So from here I get b is 1 over 2. Since I have a and b, I can put it back in any one of the equations. I'm going to pick equation number 1 because the coefficients are all 1. So I'm going to get 1 is equal to a is 1 over 2 plus b is 1 over 2 plus c. Now 1 over 2 plus 1 over 2 is 1 plus c. So this means that c is equal to 0. So my equation becomes t sub n is a, which is 1 over 2 n squared, plus 1 over 2 n, plus c, which is 0. Now I can factor 1 over n out, so I get n plus 1. So this means that this one is the explicit formula to generate the number of dots for any particular diagram.